Hello, I'm Mark Lambie. I am a consultant in Stoke, and I'm going to talk about the evidence for biocompatible solution usage. So I'm going to break the talk up into talking about what the problem is that biocompatible solutions have been developed to try and overcome, what the differences in the different solutions are, and then moving on to what the clinical evidence for efficacy of these solutions is. So just starting off with why these solutions were developed. Basically, the main problem is that dialysate or dialysis seems to be injurious to the membrane. It was pretty obvious really pretty early on. So this is data from 1989 and 1993. And on the left, you can see the graph just showing the effect of adding dialysate compared to saline to rats. And you can see in the bottom graph that the neutrophils clearly infiltrate very quickly and resolve quite quickly as well. And in the top graph, you can see the macrophages coming in, and they take a bit longer to settle. That is actually replicated in the cells that can be retrieved from the dialysate. So this is looking at what cell types those are, and you can see the majority of them are macrophages, and there are also lymphocytes. So obviously these are the more chronic inflammatory cells, and the more acute inflammatory cells are neutrophils. So there's definitely very early work suggesting that there is a degree of chronic inflammation associated with peritoneal dialysis. There's actually a whole range of extra studies that's been done alongside that. I'm just going to show you one of the newest papers that's showing that along with all the other evidence, there's also complement activation, and that seems to correlate with some of the vascular damage that gets done. Now, the inflammation in itself, well, does that really matter? Well, probably the best evidence as to why that matters comes through specifically IL-6. So a lot of the work that's been done has been based on looking at the cytokine levels in the dialysate, partly because it's easy and you've got easy access to the dialysate, and that's telling you something about what's going on in the peritoneum. And this happens to be data from the global study, and this graph is comparing the dialysate concentration to plasma concentration of IL-6. Anything above that bottom line is somebody who must have local production of IL-6. And you can see that the vast majority of patients do have local production of IL-6, and some of them have extremely high concentration gradients from the dialysate to the plasma. True also for other cytokines to a degree, but not nearly as strikingly so as it is for IL-6. And the significance of that is that's associated with solute transport. There's actually quite a lot of studies, I don't have time to show you, but a lot of those studies demonstrating that IL-6 is associated with solute transport. And there's quite a bit of evidence actually to suggest that's probably causal. We can't say that for absolute definite at the moment, but it probably is. And that's partly through taking lots of different strands of evidence and triangulating them, see if they all consistently give the same message. And that probably is true. So Mendelian randomization, which in itself has a fairly strong causal inference, did find that changes associated with higher IL-6 production were associated with faster solute transport. There's cellular evidence, there's histological evidence, and there's mechanistic evidence, such as the IL-6 now being associated with angiogenesis via things like VEGF. And then there's the sort of evidence I showed you from the global study where actually when you adjust for everything else, IL-6 does seem to be the strongest association with solute transport. So if local inflammation is driving solute transport, does that matter? Well, solute transport has been persistently associated with worse outcome for patients. So this is just the meta-analysis that's been around for quite a long time, showing that there does appear to be a relatively consistent pattern. This is some slightly newer data. This is about 2015 anyway, from DaVita, and this is showing that on the left there is, again, evidence of an association with the mortality. The most striking thing here, I think, though, is that there's really not a lot of doubt that it is really quite definitely associated with hospitalization. So solute transport is definitely a marker for worse outcomes for a patient. Now, the other thing that a lot of people probably come across is that solute transport changes with time, and this is the evidence to demonstrate that. So there's a short, sharp spike very early on in peritoneal dialysis when the solute transport rises sharply. And in the longer term, this is more contemporary evidence in Simon Davies's work, but there is still basically a gradual overall drift upwards in solute transport. Obviously, these different lines are all demonstrating individual patients can deviate from that, but on average, people tend to get faster. So if inflammation via IL-6 is driving solute transport, does inflammation change? And actually, this is a paper that we're going to be publishing soon, I hope. But the Dialysate IL-6 also rises with time, as does plasma IL-6. And in fact, if you look at the solute transport over time, then the Dialysate IL-6 and the change in Dialysate IL-6 are some of the strongest determinants of the solute transport, and that the increase in that over time as well. But I also showed you that plasma IL-6 rises. And in fact, if you look at the predictors of plasma IL-6, you can see that Dialysate IL-6 and the change in Dialysate IL-6 over time are also significant predictors of plasma IL-6 levels. So that isn't proof that it's causal, but don't forget that there is a steep, sharp concentration gradient from the dialysate to the plasma. So if it's obeying physics, then it must be diffusing into the plasma. The only question is whether it's got a detectable effect, and certainly this evidence would be consistent with that. Although obviously there are other things that determine that as well. It's not the only determinant. But does plasma IL-6 matter? Well, it's been there's been quite a few studies now over quite a long time that to suggest that plasma IL-6 does matter, and it is a fairly strong predictor of patient outcome for dialysis patients. And does any of that really matter if you, well, that question then is whether you can do anything about it. And there is actually now starting to be some evidence that we may be able to do something about that. This is probably the first study that really showed it, which was the CANTOS study. So this is not in dialysis patients. This is in patients who've had an MI previously, and they were given an IL-1 blocker, which is a cytokine upstream of IL-6. And those patients that got the IL-1 blocker had a significantly lower risk for your standard cardiology composite outcome. So, and that's actually been followed up by 2 studies now showing that colchicine, another anti-inflammatory, does appear to have significant cardioprotective effect. So there does appear to be fairly good evidence that certainly in the cardiology population, you can affect their risk of adverse outcomes. So that's probably going to be one of my major drives, is to try and get a study like that, but in dialysis patients. So inflammation clearly has bad effects in terms of increasing solute transport and potentially increasing plasma IL-6 and driving mortality through both of those ways. But there's also another way that it's probably not helping. And this is showing you, just summarizing some old data from the peritoneal biopsy registry study. And it's pretty well established now that you get an increase in membrane fibrosis over time. And in fact, that increase in fibrosis probably limits the amount of ultrafiltration patients get. So everybody will have, even for the same capillary wall and the same number of pores and the same amount of water getting through, a patient with a thick fibrotic mesh rather than a thin, loose, open mesh will have greater resistance to that water flow through it. And therefore they'll get less ultrafiltration for a given solute transport. So that's reduced osmotic conductance. Now, if that's fibrosis, well, fibrosis may often lead on from inflammation, and inflammation probably is one of the primary drivers of fibrosis. And certainly there is evidence in PD that that's probably the case. So this is mouse model work with some work in the global fluid study as well to give it some clinical validity, but it's showing the mechanism through which IL-6 seems to drive fibrosis via some of the intermediate regulators, so gamma interferon and STAT1 signaling. So if there's fibrosis, what about encapsulating peritoneal sclerosis, which is like the sort of extreme end of the fibrotic membrane? And again, there's actually fairly consistent evidence that patients who are going to develop EPS compared to patients who've been on PD for as long, but don't develop EPS, those ones who are going to develop EPS do have a more inflamed membrane. So this is results from global, but it's also true in a cohort from London. And this is the evidence from Amsterdam, again, suggesting IL-6 is higher in patients who are going to go on to develop EPS. So in summary, I think we can say that the peritoneum is damaged during peritoneal dialysis. You get an increased solute transport, which is an increase in vascularity. You get a decrease in ultrafiltration due to fibrosis, as well as the decrease due to the increased solute transport, and that those changes are associated with mortality and EPS. Those changes appear to be driven primarily by local inflammation, and particularly through interleukin-6. And the causes of that are a bit less clear, but dialysate components do appear to be a significant part of that. We know that dialysate IL-6 increases with time. So in other words, local inflammation seems to be increasing with time, which is driving an increase in solute transport. And that increased dialysate IL-6 probably is also contributing to plasma IL-6, and that both the increasing solute transport and the increasing plasma IL-6 will also drive mortality. So there's quite a few good reasons to say that it's not a great thing to have bioincompatible dialysate. So in terms of the mechanisms, well, there's a variety of mechanisms that could be driving some of these problems. So the glucose, it could be osmotic stress just in the glucose, or it could be advanced glycation end products. So that's where it's a common process where sugar binds to proteins and changes them. And that's a common factor in things like diabetes, atherosclerosis, chronic kidney disease, aging, and is generally associated with adverse outcomes. Glucose degradation products, so that's something I think most people probably be familiar with, but in the manufacture of the solutions, you get degradation products in the glucose due to the sterilization, and there's a whole range of obscure named molecules. And then there's also acidity and the type of buffer. And all of those, to varying degrees, have some degree of in vitro and in vivo data to support a role impairing host defenses and injuring the membrane. So biocompatible solutions were developed to try and mitigate some of those problems. And this is just a table to demonstrate the differences between the solutions, because they're not all the same. So you've got Dianyl, which is the standard Baxter solution. So that's pH 5.5, relatively acidic, with pretty high levels of glucose degradation products, 525. The standard Fresenius one, which was Stay Safe, similarly acidic pH, glucose degradation products not quite as high, but still fairly high. The Physionyl, which is the Baxter biocompatible one, still got not great levels of GDP, but definitely better than Dianyl. And then Balance and Becavira and Gambersol Trio are the other ones that have a more obviously significant reduction in their GDPs. And then looking at the pHs of the biocompatible ones, again, they can be 7.0 or 7.4, and that can be through a combination of bicarbonate or lactate, or one or the other. Icodextrin is actually a relatively acidic solution. It does have a few breakdown products, but doesn't seem to be anything like to the extent that the glucose has. And of course, the Neutronil is a bit less acidic, but not as neutral as the biocompatible solutions, but doesn't have glucose degradation products, obviously. So those are the differences. What is the clinical evidence for the efficacy? Does it matter? I mean, that's all sort of basically fairly theoretical stuff. Well, before I go on to talk about the evidence, then the next thing to think about is the difficulties in interpreting the literature. So there's the variability in the biocompatible solutions themselves, which does make it quite difficult to compare, because there is no study that's going to be comparing different biocompatible solutions. The only studies that are compare biocompatible solutions with the standard solutions, which makes it quite a difficult comparator. You get a variability in whether they're looking at incident or prevalent patients. There's variability in the length of follow-up. Some of these effects may be time varying, so they may change depending on how long you're following them up for. Most of the studies, unfortunately, are fairly low to medium quality, which is not uncommon in the PD field. There's very limited histological data, and even when they're getting into more sort of basic science studies, then they become hard to interpret. So for instance, changes in cytokine levels, well, they can go up potentially because it's less biocompatible, so it's damaging the membrane more, which is bad, or it might even be that an increase in cytokine levels could represent a less cellular toxicity and therefore an improved inflammatory response to an injurious stimulus, which is actually in a way more biocompatible. So it does get quite difficult to interpret some of these things, and that's some of the caveats in the data to follow. The next thing is what positive benefits might biocompatible solutions have? Well, it might be better for the membrane, so you might get slower solute transport, better ultrafiltration, less EPS. You may get less susceptibility to peritonitis, or perhaps slightly more likely a better response to peritonitis. You may get less inflow pain, more tangentially, and it's slightly less likely, but you potentially could get a decrease in transfers to HD, and you could even get a patient survival. Residual renal function is another one that we'll come back to. I'm not sure that it was immediately apparent when designing the solutions that that might be an obvious outcome to look at. But anyway, unlike many of the topics in PD, there's actually enough studies to do meta-analyses, and there's two good, solid, robust meta-analyses out there. There's the Cochrane group, and there's a group from Canada that have done it. And before going on to talk about the other outcomes, I think we can say from them that inflow pain had very weak evidence of an improvement, which is based on moderate quality evidence. So it might improve things, but there's a lot of uncertainty about that. In terms of the harder, longer term outcomes, it was unlikely that these studies were ever going to be powered to give us a meaningful estimate of whether it's got an impact on mortality or transfer to HD. And the same also appears to be true for peritonitis. There wasn't a lot of heterogeneity obvious in these meta-analyses, but again, that comes partly down to a power issue. But in terms of the more interesting results, well, residual renal function actually has quite good evidence. Both studies found that there was strong evidence that both urine volume and highly likely renal clearance was better. And in fact, both of these meta-analyses had similar effect sizes reported. And the effect did seem to get more apparent over time. So up to 12 months follow-up, maybe 70 mils or so. After 2 years, the effect size in urine volume is more like 170 mils. So not trivial difference, although it's not a colossal difference in residual renal function either. One of the questions about the change in residual renal function is why would that change be there? And one of the possible explanations would be that you're getting less ultrafiltration. So the next question is, was that apparent in the studies? Well, it's much less clear. I don't think you can say it isn't, but then there's not strong evidence to say it is changed in these studies. So the one of the meta-analysis looked at the ultrafiltration you get at 4 hours in the PET, and there was certainly a suggestion that that is reduced, but there's a lot of uncertainty in that. It wasn't based on strong evidence. The other meta-analysis looked at the 24-hour peritoneal ultrafiltration, which is obviously affected by other things, and perhaps unsurprisingly, there were wider confidence intervals around that. So it may have an effect. It may have, 170 was the estimate, but it may have an effect up to 311, or may actually mean that you get 91 mils more ultrafiltration. So a lot of uncertainty there. And a similar pattern with solute transport. Again, a suggestion from this that possibly it's slightly faster in the solutions with the biocompatible solutions, and a similar story in the other meta-analysis, although this had a slightly larger effect size, more like 0.03 rather than 0.01. But they're both suggesting that there's weak evidence of maybe a small increase in solute transport. But this is just to come back to one of the problems with that kind of analysis. So you can see here probably the best study actually by a fair way was the balance study. And on the left are the graphs for the biocompatible solution. And you can see that solute transport actually starts out a bit faster than in the standard group, but it stays the same. Whereas in the standard group, it starts slower, but by the end, it's faster. And if you're just looking at a single outcome in the study and studies of variable follow-up, you can start to see that becomes really quite difficult to try and get any consistent picture from. And the peritoneal ultrafiltration would go with that again. So you start off with slightly more ultrafiltration in the standard group, and then less at the end. So it may be that there is a faster solute transport, less ultrafiltration, and that is the mechanism for driving better residual renal function. We don't know. Just to confuse things a bit more, though, because none of the randomized controlled trials in PD are ever going to be able to look over really long periods of time. That has been looked at with observational data from the global study, and there was a completely different picture that we were obtaining there, with the biocompatible solution actually starting off slower and then eventually catching up and sort of seeming to flatten out. So there's a lot of uncertainty in what the true effects of biocompatible solutions are on the membrane. There are other ways to investigate it. So as I said, you can look at the cytokines. This was looked at in the balance study. They only actually had 88 patients with measurements, but there didn't really appear to be much meaningful difference between the biocompatible solution and the standard groups. So probably not IL-6, but having said that, some of the other previous studies suggested there might have been a difference. So again, hard to know. There is histological data. So this is just non-randomized data, and they've done a case control thing where they just tried to match people with biocompatible fluid with standard fluid, and looked at various markers, and they found that there was less fibrosis, less vascular sclerosis, things like that. A bit of suggestion that maybe in the groups with a high GDP, they might have got slightly higher C1q levels and VEGF-A, but really there was quite a lot that was pretty similar as well. There was also this paper, again, from the pediatric biopsy registry, and they looked at kids who'd only had the biocompatible solutions and looked at the membranes for evidence of damage. And unfortunately, there still was fairly clear evidence of significant damage over time in that population. So if biocompatible solutions are having an effect, it's certainly not having a dramatic effect, because there's still clear evidence of damage being done. But it may have a small effect. And if it's having a small effect, it still may be beneficial, but it's really quite hard to tell from the evidence. So one of the other things you'd have to think about is whether there's any other ways you can achieve the goal of getting better biocompatibility. And there's a variety of solutions that you could approach that from. And this is one. So there's a group mostly in Austria that have taken on that challenge. And so glutamine is an important component in a reaction that's got a horrible name that I'm not even going to try and pronounce. But again, it's a sugar modification of proteins, and that seems to be important in stress responses. So what they've shown is that supplementing the glutamine with something called alanyl glutamine improved cell survival. And they've taken that then to the bedside by doing a phase 2 proof of concept basically study, which is double-blind crossover trial. And they just supplemented dialysate with this alanyl glutamine to try and improve the local cellular stress response. They chose a co-primary outcome, which was, they described it as mesothelial cell mass, which is using the CA125 appearance rate, and peritoneal immune competence, which was the ex vivo stimulated IL-6 release from cells in the 1 hour, taken from the 1 hour dialysate 12 from a PET. Now, they're both clearly surrogate outcomes, and I'm not sure how convinced everybody is that the CA125 is definitely what it's sold as, and whether it's truly a good marker of mesothelial cell mass is uncertain. But that's why they chose it anyway. And there did appear to be some difference, actually. So you can see that the CA125 did appear to be better in the group given alanyl glutamine, and you can see that the changes. So going from placebo to alanyl glutamine, you can see the CA125 on the whole goes up, and vice versa going down. And IL-6. So this is the situation where you might expect more biocompatible to mean you have more IL-6, because the cell's going to function better when you're taking it out and stimulating it to release IL-6. And again, that's basically what they found. So they're now going ahead with a phase 3 trial. But that's not the only solution that you could take. You could take a much more pragmatic solution of just saying, well, if dialysate is bad for that membrane, why don't we just try and give the membrane a bit of time without dialysate? And that can be done a couple of ways. You can just give patients a few days off, and that certainly going to be quite popular from the patient point of view. So actually probably the strongest argument for doing that is purely from the patient point, but it may also have a benefit of potentially being a bit more biocompatible. This is the only data that's able to explore that at all, because in Stoke there's a practice of using dry days quite a lot. And certainly if those patients who had dry days appear to have a slower solute transport, although it did seem to rise with time and eventually catch up. But having said that, if that's just like an area under the curve, exposure to inflammation, that still could potentially be beneficial. Hard to know. So whether or not that idea of resting the membranes really got any merit, very weak evidence so far. Another solution that's actually been published a couple of years back, which is quite appealing, I think, is blocking something called toll-like receptors. So these are molecules that will respond to what are called damage-associated molecular patterns. So these are molecular patterns that are released in response to cellular stress. So heat shock proteins are one example, and matrix degradation products are another one, so things like fibronectin. So they will then bind to the toll-like receptors, which then trigger an inflammatory response and a fibrotic response, so IL-6 and TGF and TNF and IL-8 and things. So that's potentially one of the mechanisms by which, or one of the pathways by which dialysate is driving some of this damage. So the group in Cardiff tried to explore that. And basically what they found is that there does appear to be quite a benefit. This is all, this is not human data, so this is not in human results. But you can see that where they gave just the dialysate, there was significant fibrosis. Where they gave the dialysate with the TLR2 blocker, the fibrosis was much reduced. And this is a similar pattern to all the cytokines they tended to look at. So these two columns to the left are just a control solution called phosphate buffered saline. But this is the main comparison between the dialysate and the dialysate with the toll-like receptor 2 blocker. So again, that may be another route that can be explored. And there are in fact even other dialysate solutions that are now being trialed. So there's an ongoing phase 3 trial called Elixir, which is a study of a dialysate solution that's greatly reduced the glucose concentration by using another sugar called xylitol and supplementing it with carnitine. And so that's going to be a study that's going to run over the next couple of years across Europe. So there's a variety of other ways that we could achieve biocompatibility. So although I think you can say that biocompatible solutions have their limitations, so they do increase urine volume. I think we can be pretty certain about that. So that's probably a good thing, although there's a bit of doubt about that because it may be due to increased fluid loading. So we don't quite know. It may decrease peritoneal ultrafiltration via increased solute transport. It probably decreases inflow pain. But compared to the drivers of the damage, the biocompatible solutions have relatively minor effects, and these other strategies do exist, but clearly requiring more evidence. So I am going to stop there.